Welcome to this course that is about the introduction to the ICRP and model-based dosimetry. My name is Silvano Gnesin. I'm a medical physicist at the Lausanne University Hospital in Switzerland. So at present, I have no conflict of interest to disclose. Here the context of this presentation. So I would first introduce the ICRP, so what it is and what it does. And then I move to dosimetry methods that are employed by the ICRP. And in particular, we would focus on the difference between model-based versus personalized dosimetry. And then we go through the evolution of reference human models that are used in the SRP dosimetry calculation. At the end, I will provide an example of dose exposure from radiopharmaceutical for a common case of F18 FDG. So let's start. Just try to understand what ICRP is. So ICRP is an International Commission of Radiological Protection, that's why the acronym, and it is an independent international non-government organization. The aim of the organization is to protect people, animals, and the environment around the world from the possible harmful effect of radiation. What ICRP does? So ICRP works in a structure that is composed by different committees. So we have Committee 1, that is about radiation effects and consider the effect of radiation action from the subcellular to population and ecosystem level. It includes the induction of cancer, hereditary, and other disease. The second committee is about dose from radiation exposure and develops dosimetric methodology for the assessment of internal and external radiation exposure. The committee 3, that is the most interesting for nuclear medicine application, is radiological protection in medicine that address protection of person and unborn children when ionizing radiation is used in medical diagnostic, therapy, and biomedical research, as well as protection in veterinary medicine. And then we have Committee 4, this is the application of the Commission, so it provides advice and of the application of the Commission recommendation. And in general, ICRP recommendation form the basis for radiological protection policy, regulation, guidelines, and practice worldwide. So about model-based versus personalized dosimetry, we have to point out that the ICRP use models representative of standard human subjects, so are not exactly is an average that holds for the average adult, in this case, patient or subject. So ICRP 110 publication reports these phantoms. And as you can see, you can have in the real life different patients' size and shapes that are not represented by the phantom of the ICRP. And these ICRP phantoms are used to define the S value in the absorbed dose formula here. And also ICRP provides standard radiopharmaceutical biokinetics in order to be able to estimate the integrated activity per unit of administered activity. So it defines this the A tilde value. And also you can see here that between the model that is used by the ICRP and your actual patient, that could be discrepancies. Indeed, ICRP provide references for a model-based personal dosimetry with the reference person, reference subject, and it's not exactly your personalized dosimetry that is addressed. So ICRP also provide standard SAF, so specific absorption fraction, that are listed in this ICRP publication 133. and it enters in the formula of the S coefficient that are computed with Monte Carlo in the reference model geometry provided also by ICRP. As you can see, the specific absorption take into account for the fraction of energy of radiation, the type R, emitted within a source tissue Rs that is absorbed in unit of mass per unit of mass in a target tissue RT. ICRP also define reference dosimetry models also in terms of biokinetics. So the biokinetics can be defined by using data from sequential imaging, as is performed in some dosimetric studies. And also biokinetic can be derived from samples, so biological samples such as blood, excreta, salives, and so on. There are also some limitations of these biokinetic models because they are built using a limited number of restricted information that are from the clinical studies that are collected around the world, but this clinical study often refers to restricted population that is, in most of the case, the Eurasian population. So we have to take into account that there are these restrictions in the representativity of these models. Biokinetic models, so collected and established based on imaging, biokinetics, imaging derived, and sample-based biokinetic in a certain population, is used to be implemented in the biokinetic models with blocks that represent different tissues. Here, for example, typically in nuclear medicine, we inject a certain amount of radiotracer or radiotherapeutics through the blood, and then it reaches the tissue. So the simplest representation is here with just two compartments and kinetic coefficient that links the uptake of the tissue and also the washout from the tissue. But of course, these kinetic models can be much more complex, as it is in this example for F18 FDG, or in this other example that is also reference ICRP compartment model that is valid for iodine. Other incorporation pathways, in addition to the administration by intravenous or intraarterial administration, can be inhalation, ingestion, and wounds. Let's move also to the concept of equivalent dose H and the effective dose E that is provided in many of these ICRP publications. So the equivalent dose H for a given target tissue is the sum of the absorbed dose, so the physical dose that is still in gray, from all the source that contributes to the dose to the target, weighted by a factor R that represent the radio induced effect of a given radiation, R, that can be alpha, gamma, beta particles, ions, or neutrons. And as you can see, these tissue weighting factors varies from 1, this is the case of X-rays beta particles, till 510 for alpha particle heavy ions, up to similar values for neutron beams. As you can see, this value are according to the knowledge, to the present knowledge at a certain time of the radio-induced effect of a given radiation. So it might change also in the time according to the actual knowledge. And that's why this quantity is not more expressed in grade by in sievert, because it's ponderated with this radiobiologically defined weighting factor. And also we have the effective dose, that is the extension of this concept, when we also consider that different tissue into the body have different response to a certain amount of absorbed dose. And then we ponderate the equivalent dose to obtain the effective dose with this W with T. factors that also can change with the knowledge that we have from radiobiological study and population study. As you can see here, in between 1975 and 2007, this value changed for different tissues according to the knowledge. And also this is expressed in sievert. And this quantity, H and R, are no more absorbed dose, but especially the effective dose is used for estimating stochastic risks. So the appearance, the potential appearance of radio-induced disease with time in a certain reference subject. Radiation dose to patient from radiopharmaceutical. So the scientific knowledge on radiopharmaceutic evolve with time, and then also biokinetic model are improving in this ICRP framework. We have that improved knowledge on radiobiology and dose effect relationship is also updated with time, and that's why we have appearance of different ICRP publication about the radiation dose to patient across time. So since the publication 17 in 1971 up to publication 128 in 2015. Okay, now we move to the evolution of the reference human models, because ICRP adopt reference human models in order to have the geometry of the body of a reference human body and the tissue terrain in order to compute, for example, S factor and then absorb those to tissue. Here you can see the reference person in ICRP publication 23, and that time 25 target region, 25 source region were evaluated, and as you can see, the geometry is not too much realistic as we can have in the present days, and the organs are mainly obtained by geometrical box or ellipsoids. Of course, there was already the idea to implement models also for pediatric subjects. In the reference human model provided by ICRP, it is important also the publication 89, because it defined the age and gender related anatomical and physiological characteristic of the reference individuals. And you can see here that for different models, so also pediatric models, are provided elemental composition of tissue, the masses of the different tissues. And of course, we still have to keep in mind that this was information that are derived from Western European and North American, so Eurasian population. So this can be a limitation of this methodology. The evolution of the reference human model happens during the time with the ICRP models. And now at present, we have adult reference voxelized phantoms that are defined in this ICRP publication 110. We have the reference computational models that are based on voxels that are obtained from medical actual patient medical image data. And the masses of this and composition of the organs and the tissue in this model are consistent with publication 89. Typically, softwares that are used for organ-based dosimetry, that can be commercial or also free software for research, use this reference phantom with ICRP 89 referred organ masses and compositions. Also, pediatric models have been developed not only for reference adult male and female, but also for pediatrics. And we have at present a voxel phantom for pediatrics of different ages. In the near future, so there is the study of new pediatric mesh type reference computational phantoms, as you can see here. So not only pediatrics, but also for the adults. And this is, they are coming soon in publication with the ICRP publication 156 that is not yet published, but is in preparation. The mesh reference computational phantoms have some advantages as compared to voxel phantom, because here the structures especially small details of structures, can be considered in a more realistic way and with adjustable scale according to the needs. So you can really move much closer to the reference subject to a specific patient like geometry. And here you can see which is the detail that we can achieve with this mesh reference computational phantoms. Also here, some details of the accuracy of the geometry that we can get with the vascular system, with the lymphatic and the skeletal systems, and the muscular system that was not achievable in this accuracy with voxel phantoms. Also, pregnancy reference model with mesh phantoms are of interest for ICRP, and ICRP is working to provide this mesh reference phantom for pregnancy periods in different parts of the pregnancy period. So here at 10 weeks, at 20, 30 weeks pregnancy for the female phantom, and you can see the detail that we can obtain also for the fetus and the baby, and also we take into account the possible upside down geometry of the newborn at the end of the pregnancy period. Now I would focus on the way the ICRP defined the effective dose in order to provide estimation of stochastic risks in a reference human. And you can see here that we referred in this case to ICRP publication 103 that defines the methodology to define the effective dose for the reference subject. The reference subject is in terms of effective dose, a weighted sum of the equivalent dose of tissue from male and female adult reference phantoms, weighted, of course, with the radiobiological defined WT tisular ponderation factors. So when you have the dose in tissue for the male and female reference phantoms, you weight it then with the, you take the average and weight it with the WR and then with the WT ponderation factor, and you obtain the effective dose that is not for a realistic patient that you have, but this is for the gendered average humans subject. And this is used for extrapolation of stochastic risks. And now at the end, I provide you with an example of a common used radiopharmaceuticals. So here we consider F18-FDG that is used for most oncological PET diagnostic examination. And here you can see tables that are present in the ICRP publication. This table is from the ICRP publication 106. And you can see that we have two parts, one part that concerns the absorbed dose in reference subject, adults and also pediatrics. So for each organs and each phantom model, you have the absorbed dose in gray for that models. And at the end, by computing the average ponderated sum, that we obtain the effective dose for the reference subject. So just an example here, you have your patient, let's say a patient that you have in clinic with 33 kilos, you used to administer 3 megabecquerel per kilos in that patient, and then the actual administered activity would come to be 219 megabecquerels. And you can see here for the adult patient, you have 1.9 is 19 microsievert per megabecquerel, and then you multiply this number for the megabecquerel that are administered, and you obtain an estimate effective dose for the reference human adult subject that is of 4.2 millisievert. And you use the information that the probability of induced fatal cancer in a population of all ages is 5% per sievert. And then at the end, the probability of radio-induced fatal cancer for that patient is of order of 1 per 1,000. So you have in this case an estimate of the stochastic risks. Sorry. And this is the example I would provide in this reference case. So we can move to take-home messages. So ICRP provides a reference for radioprotection and dosimetry with radiopharmaceuticals. ICRP also focuses on radioprotection of population. And ICRP defines realistic reference anthropomorphic model and reference pharmacokinetic model for absorptors calculation. Evolving knowledge is incorporated in new ICRP publications that are regularly updated with time. We have also to mention that so far ICRP focuses mostly on the diagnostic use of radiopharmaceuticals, and the model-based, the model for dosimetry that are used by ICRP are key for clinical protocol optimization and the assessment of stochastic risk. So I thank you for your attention and enjoy the rest of the courses.